Yeah, just really happy to be here, and I think this will be good. I hope you guys enjoy it. I'll introduce myself further on in the talk, um, but yeah, let's get going. So, providing yield insights to farmers at scale. Uh, so yeah, just an outline of what we're going to discuss and the ground we're going to cover. So, first is what is the problem and why is it important? What can we do about it? So think about the solution space, how aerobotics solves this, the aerobotic solution, and then the system that powers the solution. So basically, the software engineering component of everything. Cool. So a bit about myself. I'm a software engineer at Aerobotics. I work on our platform team for the last couple of months. But initially, I worked as a data scientist on the team building our yield product. I'm passionate about the intersection of software engineering and machine learning and how we can leverage it to create solutions that improve the world around us. I do very intermittent writing at senyoSimpson.com and tweet very annoying tweets at SenYusers if you want to check me out. Cool. So hi from Aerobotics. Aerobotics is a tech startup building the next generation of smart technology for the agriculture industry. We provide farmers crop and yield insights using aerial drone imagery, computer vision, and machine learning. If we added the buzzwords like blockchain, I think we'd have it all. And yeah, you can look up a bit more about us at aerobotics.com. So yeah, Aerobotics, we collect and analyze the most complete, accurate, and timeless tree crop data. Up till now, we've counted and analyzed over 120 million trees, detected over 10 million fruits, and identified over 80,000 pests and diseases. So yeah, this is pretty amazing. Cool, so getting into it. Farming's big problem, yield estimation. So what is the problem? Obviously, yield estimation. But yeah, basically traditional yield estimation is an extremely labor-intensive process. This process includes like counting and measuring each fruit or sample of fruit from a few sample trees. Then you extrapolate that to the whole orchard to get, or farm, in whichever dictionary you want to use, to get an estimate of the total number of fruit in the orchard. And then you want to project that into the future to get a yield estimate. This process is subject to high error margins, and you can imagine kind of like the amount of data you need to get a good enough estimate there. And it's also difficult and costly to develop methods to improve upon this estimate for individual farmers. It's not, in their core competency, and it requires a lot of effort and money and time. And so, for each individual farmer to go through that process to the degree which would make it quite a practical is a big endeavor. So why is yield estimation important? Money, of course. But just talking through it. So basically what happens is early on in the season, farmers will inform buyers of their expected produce. And that produce is sold at a premium price, while any excess is sold at a second-rate price. And so, if they underestimate, they lose potential revenue. So for big farms, that can be in the millions of rands, for our US clients, obviously in the millions of dollars. And if they overestimate, they pay penalties to the buyers, since the buyers cannot fulfill their obligation. And so this leads to very conservative estimates. So for instance, they'll say, 80% of the expected yield is what they'll tell the buyers in order to minimize the chance of getting a penalty. But it does leave a lot of potential revenue on the table. So additionally, this also allows them to plan interventions to maximize the yield. So if they get this data early on in the season, it can facilitate their decision-making process to ensure that they get the right, or to ensure that they maximize their yield at the end of the season. Cool. So what can we do about it? Absolutely nothing, unless you're Aerobotics and you're willing to take the challenge on, I guess, plus a few of our other competitors. But cool, so 1,000-foot view, I just want to walk through kind of like what yield estimation looks like and kind of like the steps involved, and then where this talk will go and what we'll discuss here. So initially, from an orchard, Sorry if there's so much noise. It's people outside. So yeah, so from an orchard, you'll sample a set of trees, and on those trees, you'll count and measure a bunch of fruit, either all of the fruit on the tree or a sample of them, and basically extrapolate out to the tree. Then you'll extrapolate to an orchard-wide estimate. So this will give you like the total number of fruit across your whole orchard. And then you'll have basically an histogram saying, like 40% of my fruit are between 40 and 45 mils. And so that will give you basically like a size distribution of your orchard. Then you want to project that to the future. So that will obviously tell you at harvest time, this is, so maybe at the beginning at the time taken, you'll have 40% of your fruit between 40 and 45 mils. And then at harvest time, you'll have 50% of your fruit between 60 and 65 mils, for instance. And so that's the projection. Then you want to map sizes to a weight so that we can say, 55 mils equals whatever, 30 grams, for instance. And that allows us to get a tons estimate at the end so that the farmer will be able to say, like, I'll have, 100 tons of fruit between 60 and 65 mils at harvest time. Cool. And so, yeah, most of this talk is going to center around how we collect and analyze this data, and then the counting and measuring this fruit, where successive talks in the future will get into some of this other stuff when we're open for that. So yeah, just walking through the solution space. So this kind of just going to walk through like some kind of like ways we can think about solving this. This is relative to our context at Aerobotics, so using the kinds of data that you would use. And yeah, I mean, there's obviously alternative approaches, but I won't delve really into them. Cool. So yeah, our first option. So based on historical data, we can make an estimate. So, like last year, maybe I got 50 tons of this, and this year, like the weather's the same and soil's kind of the same. And so I'm expecting to get the same amount this year. So the advantage of that, obviously, I mean, it's fast. And I think that's possibly the only advantage, the only one I could think of. So disadvantages, obviously, it's an extremely crude estimate. I mean, nothing much went into it other than last year's or maybe a few years before. Alternatively, you can think about it like it's quite a good heuristic, and humans are quite good at that, but we haven't taken any information. And so this does not take into account any present day environmental factors. And so by that, I mean things like, let's say, like soil health, or the moisture of the soil, or like the weather that's been going on at present or over the last season. And so that all that information is kind of like discarded in this one, and then it's inflexible. So if things change over the course of the season, then your models are obviously outdated. So, if last year, or if this first half of the season this year is the same as last year, and then the second half is completely different from last year, our models obviously, all the assumptions it was based on was violated. So yeah, that's an inherent disadvantage of this method. So option 2, so based on a sample of trees, we manually count all of the fruit and measure their sizes. So, okay, and then we extrapolate that estimate to the rest of the orchard, and then we project that to the harvest date. So the advantage here is that it uses some contextual information. So we're using like the size and number of the fruit per tree, for instance, and it can incorporate historical information for a more precise estimate. So we can take like what we know about the scene or the farm today, plus some historical information, combine them together to get a more precise estimate. So you can kind of think about that like a Bayesian way of thinking with the prior and evidence. Some disadvantages: it requires extensive manual effort. So yeah, counting fruit manually it takes time. Like it can take 3+ hours quite easily for just one tree, and obviously you have to measure them as well. So it really is like a labor-intensive process. Difficult to sample a representative set of trees. So in an orchard, you can think that like maybe there'll be like micro regions which are slightly different from each other. And in those regions, maybe like, one region will have fruit that are on average maybe like 2% bigger than, another region in your farm. And so, yeah, just given that, like, obviously you want to sample each of the, like, sample from each of these different sort of like regions. And so, yeah, it's obviously difficult to get that right. Cool. So option 3. So based on a sample of trees, we sample a set of fruit and measure their sizes. So different from option 2 is that we don't count every single fruit on the tree. We just count a sample of them. Then we extrapolate this to the tree level to get an estimate of the total number of fruit per tree. And then we extrapolate that to the rest of the orchard. And then we project that to the harvest date. The advantages here is it requires less manual effort. So, we could probably figure out like the least amount of fruit we need to sample to get a decent estimate of the total number of fruit on a tree. And that will be significantly less than that counting every single fruit. It allows us to take advantage of tree level information. So, like if we've been able to find out like the radius and area and volume and heights of the tree, we can use all of that information for that specific task, but possibly down the line as well. And it's also useful data to collect, so good side effect of that process. And then it's easier to automate. So if you don't have to count every single fruit on a tree, you can use different ways of collecting that data like drones, hint, hint. And cool, so some disadvantages there. So it's difficulty in sampling a representative set of fruit. So, like from the tree itself, we have to sample both small fruit, big fruit, like medium-sized fruits. And there could be some biases depending on which side of like, for instance, if you sample mainly on the surface, it might have, those fruit might be like bigger than ones on the inside of the tree, for instance. And so you have to really, again, sample a representative set of fruit, and then also trees in terms of the whole orchard. This also requires tree level information. So getting this data can be quite laborious. Luckily for us, we have a product that allows us to collect this data, but doing this manually again also takes a lot of effort. So option 4 is obviously to give up. So obviously a nice and easy solution, but it comes with all of the disadvantages that comes with that, and obviously that's not a feasible solution. So cool, the Aerobotics solution. So the way we're thinking about it. So yeah, firstly, the challenges, just laying them up front. So a big challenge for us is probably one of our most significant ones early on in the process is just the precision. So fruit need to be accurately sized within 3 millimeters. This is kind of like just the tolerance that we found allows us to make any sort of like decent estimate. And also obviously customers don't want to hear that their fruit is like 51 mils when it's 45, or actually the inverse, we say it's 45 and it's actually 51. So yeah, within 3 millimeters, and then obviously like errors can get propagated down the line. So if you start off with like a 5 mil, or let's say like 7 mil error, that could end up with like a tons error of like 10 tons, for instance. And so yeah, we have quite strict precision bounds for fruit sizing. Data collection is expensive and difficult to scale. So yeah, at Aerobotics, we invested tirelessly in our process, and yeah, just being able to do this efficiently. And so yeah, it's something that we've had to overcome, but it really is a difficult endeavor to get this data, and extremely expensive. And on top of that, just compounded by the fact that there's no data set like this in the public domain at present. So there's nothing that we can kind of like leverage off or use that's publicly available. And so we've kind of had to be like, or effectively like pioneers in collecting this data, which again, then incurs the costs and of doing so. Yeah, then another challenge is modeling natural processes. So this requires a strong understanding of agronomical factors that impact like crop production. Yeah, and it's just something that is difficult. There's not as much research as we'd like. And so yeah, we're also investing a lot of time and effort into learning more about it. Cool. And then yeah, a big challenge from the machine learning side is just handling a surprisingly wide distribution of data. You would think that like all trees in an orchard are the same or look the same, and therefore this wouldn't be the case, but you'd be surprised how much it varies in farming. And so yeah, a big one is like in-farm variance. So like I was saying, like certain like micro regions could have slightly different characteristics from others. And then a cross-farm variance, which is compounded by two things. One is that we have clients both in South Africa and the US, and they have different weather conditions and climates and all that jazz. So cross-farm variance is a huge thing. And then another one is that different farmers have different practices. And so all those different practices can lead to different outcomes with their yield. And so, yeah, accounting for those is something that also we're still very much invested in working on, but it is something that's quite a big challenge. So yeah, just on how we collect data. So initially we set up a flight path for our drones using our orchard mapping data, which is our other product. For our purposes, the most relevant information there, at least for this specific task, is that we have found every tree in the orchard at this point. Flights are allocated to pilots who go out and fly the drones for us. And then the drone captures videos for each tree sample. We process that imagery, and then that's available on our front end. So size and color information is generated in AeroView, which is our web platform, and that's ready for export or for our clients to view on the web platform. So cool. So yeah, as I said, I was going to chat through like our fruits housing work and again how we collect data. So this is just kind of like an overview of how it works. So drone imagery is uploaded, as I said before. We detect and segment fruit on each tree that we process. Then we apply post-processing, which I'll go over as to why and like what post-processing we do. Then we size the fruit and then project to harvest, and then client results are available for the client, of course. So yeah, just walking through a visual representation of what this looks like, because I think that's the best way to kind of understand this process. So initially we have this drone imagery here. And yeah, the next step is to detect, detect fruit and yeah, basically that. And you can see here in the image that there's these red contours around all of the detected fruit that we found. Also, interestingly enough, you can see that here there's some of the rocks have been detected as fruit. And yeah, I mean, like we can assume in these cases that like the model uses shape as like a huge indicator for a strong indicator for fruit, maybe versus color. And so yeah, so for this detection, we use deep learning to perform intersegmentation. It's obviously probably the best method to use for this. So you can think of models like Marscal-Senyo or RetinaNet. Yeah, basically that for intersegmentation. And these are trained on human annotated images. So obviously, like in the beginning, we had a cold start problem, and so we did a lot of annotating. But now we've kind of got this like flywheel of data. So basically, what will happen is data will come in and be processed by our models, and we have a lot of like automated checks on quality. And so if we can flag that some data isn't up to standard, we'll send it through human QA, which might get annotated or re-annotated. And in those cases, and so we use a lot of that data for our reference data for training. Some challenges here. So occlusion's a huge one. Fruit being partially hidden by a leaf. And so you'll get these like really weird contours that are like half the fruit, which technically is correct. But obviously there's a fruit behind this leaf. And so that was quite a big one. And then false positives. False positives, yeah, tend to be there were problems, quite a significant problem early on, but I mean, we've obviously developed a model, but there's still some room for improvement there. And so we've kind of thought of post-processing as a solution to that. So post-processing, you can see in this image that like the rocks that were there have been removed. And so, yeah, so for that specific task, we use a binary classifier, which predicts fruit or not fruit. And yeah, the reason why we've taken this approach is just because that's a very like specific objective. So you can think that the intersegmentation model is doing both detection and segmentation, and it's a very complex task to learn, and also just given the complexity of doing it on fruit imaging. And so we found that having like a very specific task to just do the fruit, not fruit right at the end after all of these predictions has really has proven to be effective for us. And yeah, I think it's like one technique that we've really sort of like invested some time into doing. However, there's a lot of overhead in managing two models that could effectively be one, just the intersegmentation model. So things like, yeah, just updating both models and monitoring both models. And if you change the upstream model, you've got to change the downstream model, and you've got to evaluate both of them, or the output of the dual model, basically, to prove that an update is actually better. And so there is some overhead there, but for us, it's proven to be quite effective. And so like the intersegmentation model, our most important thing there is the recall, so we can find it with fruit, and then the post-processing is precision, so that we can just make sure that we've cleaned out any of the false positives that we found. Cool. And then the last part is sizing the fruit. I don't know if you can see, it's quite small, but next to each of these contours now is like a size. So like, for instance, here it's 40 mils, that's like 31, 36 mils, 39. And so, yeah, this is just like the output of our fruit sizing algorithm. That uses stereo triangulation. So that allows us to map from a pixel width and height of the fruit to like a physical height and width. And then obviously taking like distance into account, and like how much the like a per pixel width changes with distance, etc, etc. So that's just like classical computer vision and a bunch of mathematics to get that done. And yeah, using stereo imaging basically. Challenges there, so finding the corresponding fruit in each image pair. So I mean, that's just a problem in general with stereo imaging algorithms, is that you got to find matching points in both images. And so yeah, for us, that in most cases it's all right, but there's some cases where if you have, for instance, like a high density of fruit in a certain region, it makes the problem quite difficult to solve. Luckily for us, you can kind of think about this as like, if you think about each fruit in 2D space, you can think about it like a point cloud registration algorithm. And there's a lot of techniques that can be done there. And then, yeah, inaccurate matches can skew results. So when that happens, when you have inaccurate, or when you have mismatched fruit, then you can often get like very absurd sizes out. Which those you can filter, but in the cases where they're not totally absurd and like they can be difficult to identify, and in those cases it can skew results somewhat significantly. So yeah, and then yeah, at the end of that process, there's the client data. So client will get out a bunch of data or get out a report like this. So this is like at the time of flight. And you can see here at the bottom with these fruit sizes, for instance, between 41 and 43, there's 15% of the fruit lie within that range. And so, yeah, that's useful for farmers, because normally these sizes map to like a label, which can be like, you know, a grade A fruit or grade B or whatever they want to, whatever they classify it as. And so they can easily tell like what distribution of fruit lie, or what the percentage of fruit lie in certain like buckets that they care about. And so yeah, so this is a file report, and then once this is projected to harvest, they'll get a similar report that will then obviously say like at harvest time you should expect 20% of your fruit to be between 58 and 60 mils, for instance. So yeah, so that's pretty much a run through there. And then just going through the yield system itself. So how did we build it? So our tech stack is predominantly Python. So for our backend services, so we're actually adding data science, I guess. So a lot of Python for us. Django is used for all of our services. TensorFlow for our deep learning efforts, and again, all the scientific Python libraries for everything else. we run all of our stuff on top of Amazon Web Services. And yeah, we use Terraform to basically manage our infrastructure as code. Cool, so 1,000-foot view of our yield system and what it kind of has to facilitate and what it does. So we have batch processing workloads. So, you know, a bunch of data will come in and then it's just got to chug through a bunch of that data. And these for us are characterized by bursty workloads. So we'll have a bunch of data come in and you know, that is great, chug through at that time, and then there'll be a lull and then be quiet for a while, and then again, like a bunch of data that comes in. Cool, and these spin off a pipeline per unit. So a unit being something that obviously you want to parallelize on. So we can say that you want to have a pipeline per farm or per sample or like per tree, for instance. And so, you know, that's kind of like a requirement that we need just to make sure that we can process our data sort of like effectively. Cool. So on average, we process around 600 hectares a month, reaching 3 times that in busier months, so about 1,800 hectares. That doesn't seem like much sometimes, like when you say it, but 600 hectares is about like 600 rugby fields worth of data, basically of image data. And so, yeah, it's a bunch of data to get through. Cool, and then that generates between 8,500 and 12,000 pipeline executions, which again might not sound too crazy, but I mean, all of these pipelines are doing really, really big computational tasks. So we have deep learning in there, we have a lot of the stereo triangulation methods in there, and so it's doing quite a lot of heavy lifting within those pipelines. So it's quite a bunch of work that we're doing. So some challenges there. So big one is efficient utilization of compute resources. So with bursty workloads, you'll have a bunch of data come in, and then obviously all of your resources are used basically to the max. And then when it's finished, then there's no utilization of the resources. So that's a problem or a challenge there. Another one's handling high pressure bursts in our system. So a bunch of data will come in and all at once, basically, and obviously like AWS has limits on like how fast it'll spin up new instances or how fast it'll start new step functions or whatever. So it just puts a whole lot of pressure on our system at a point in time, which can be difficult to handle. And then obviously another thing for us is just parallelizing jobs. So we don't want to have one like worker chugging through a bunch of data when we could parallelize over some unit. And so, yeah, that's another one. So for us, like the solution, what we need is serverless. So we need something that's serverless, that has back pressure in a sense, and can easily run multiple execution pipelines. So for serverless, obviously that gives us like dynamic workloads or dynamic compute, so that we can use compute when we need it, and then once our work is done, then it's like shut down for us, and so we don't actually waste money with provisioned resources that are not being utilized. And then back pressure. So back pressure just being that we slow the flow of the execution basically onto step functions, and so that you know, it doesn't take down our systems or cause a lot of failures, basically, and then obviously running multiple pipeline executions. So our solution there, I've mentioned a few times, is coming through here, is step functions plus Fargate. So step functions and Fargate work quite nicely together, and then SQS, the simple queue service by Amazon, just for sort of like our back pressure needs. So step functions, there it defines a pipeline for batch workflows and is easily parallelizable. So yeah, we use step functions. So we have a bunch of state machines that then execute one after each other. And we can define that whole pipeline within step functions itself. And then we can trigger that based on obviously some core unit of work, whether that's a farm, orchard, a tree, or whatever. So that works really well. So step functions is for that kind of like batch workflows. And then we run that on top of Fargate. And so Fargate itself is a serverless compute engine. And so that's, the provider for step functions. So then we can trigger jobs. They'll run with the necessary CPU resources and memory resources and storage resources, and then shut down when it's over. And so we found that combination quite good, fairly simple to use, and has led to quite a big cost savings versus us provisioning instances that weren't being used when work wasn't being done at points in time. And then lastly, we use SQS for unintelligent back pressure. I say unintelligent mainly because we just use a delayed queue. And so basically jobs will be launched onto this queue and then they'll be delayed by a certain amount of time before being popped off. So that just allows us to not hit our limits on or our AWS limits on how fast we can spin up new step functions. And it's unintelligent because it doesn't really take into account how much work is being done at present or any of that jazz. But it's been fine for us up till now. And so we've had no pressure with needing to implement anything way more sophisticated at this point in time. But we are expecting it to get there relatively soon. Cool. So yeah, that's pretty much it. At Aero, we always say every tree counts. And yeah, cool. That's me.